Hello, everyone. So this is going to be about MCMC and couplings. This is joint works, and I will acknowledge, of course, my collaborators throughout the talk. So I'll delve right into the setting, which is just the MCMC setting. So you have a target distribution, so it's a probability distribution denoted by pi, and you would like to sample from it, and you don't know how to exactly sample from it, so you design a Markov chain that will asymptotically converge to pi. So you start from some distribution pi 0, and then you generate xt given xt minus 1 according to a distribution denoted here by p xt minus 1 dot. So that depends on xt minus 1. It's called the transition kernel of the algorithm. So any MCMC algorithm translates into a choice of Markov kernel P. So this is the question that we'll be looking at. Essentially, how many steps should we do when we do MCMC? So in other words, how do we choose a little t so that the marginal distribution of the chain at step t, denoted by pi t, is close to pi in some sense? So that in one way, it's related to the convergence of those marginal distributions towards pi. And in another way, it's related to the convergence of the ergodic averages, so the estimators that you obtain from your MCMC. If you have a test function h, that would be, for example, an indicator or a polynomial, or the identity function if you're interested in the mean, towards what is denoted by pi of h, which is the expectation of h of x when x follows pi. And we expect in many cases when we do MCMC that there will be some central limit theorem, but we might not know exactly the value of the asymptotic variance denoted by Vp of ph here. So it depends on the Markov kernel P, and it depends on the test function h. And if we knew about it, we would be able to construct, for example, confidence intervals. And again, like in order to know how many steps to perform, it's useful to know what is the associated error. And so essentially, we want to know how many steps to perform in the sense of either the marginal distribution is close to pi, or the ergodic averages are close to their limiting values. So that's the sort of high-level questions that we're going to try to address with couplings. And so I'm going to use a very simple running example where it's a location model for where theta is a location of a Cauchy distribution. We observe some x's, and we put a Gaussian prior on theta. And so you can write the posterior distribution of theta given x as priors times likelihood. And then there's a nice little trick where you introduce variables denoted by eta. It's a data augmentation classical trick, and so leads to a Gibbs sampler where you would sample the etas given theta from an exponential, and then the next value of theta prime, given the etas, as it happens here from a normal, and so it's very simple to implement. Yeah, so it's a Gibbs sampler, and then you specify an initial distribution, and you have your MCMC setting. So what does it look like? Well, so this is the target. There's a histogram of samples from the target and the density overlaid. Don't know if you can see it. So it's a trimodal distribution. Here there are just 3 observations corresponding to those 3 modes. When you have more and more observations, it becomes more like a Gaussian. But it's kind of more interesting with just 3 observations. It's really a multimodal. Okay, that's an example taken from a review article on convergence diagnostics from '95 by Christian Robert, who was my PhD advisor. And this is a trace plot of that chain on the theta scale, right? So at every step you sample eta, and then you sample a new theta, and those are just the thetas. You can see they move from one mode to the other. There are 3 modes. You can sort of see it from the trace plot. And so again, from this, you can visualize this. It's nice and easy. Here it's one-dimensional. Of course, in realistic scenarios, your chain lives in a high-dimensional space, and maybe it's a complicated space to visualize, like a space of trees or a discrete space or something. But here you can visualize this, and but still it's not obvious, right? For one trace, how many steps are enough? It's kind of the first thing is like it's not obvious to know when to stop the chain. And so couplings is a way of addressing this question. So I won't assume any prior knowledge. Just one of the appeal of it is that it's simple enough so that we can actually understand it without having done hours of studies on the topic. So the key idea is to, in order to study the convergence of our chain denoted by xt, to introduce another chain denoted by yt. And this one is assumed to be already at stationarity in this original introduction of couplings. So we have xt and yt is at stationarity, whereas xt starts from pi 0, so it's not at stationarity at any fixed time t. And they're both marginally evolve according to the Markov kernel P. But we can maybe construct them in such a way, and that will be up to us to do this construction, in such a way that there will exist a meeting time, so time tau, at which the chains become exactly identical, even on a continuous state space, and then remain identical. Obviously, there's not going to happen by chance if you don't do anything special about it, especially on continuous state spaces. On discrete state space, you could hope that just by chance they will end up exactly at the same place, but in continuous spaces, you'll have to work a bit to see that. So the slide shows some sort of cartoon trajectories that might be of the type that we want in the coupling study. And then the idea that dates back to the work of Wolfgang Döblin in the 1920s is to upper bound the total variation distance between pi t and pi as follows. So you first note that it's the marginal distribution of xt and the marginal distribution of yt, right? Because yt is assumed at stationarity. And then you can always upper bound the TV between the two distributions by the probability that xt will be different from yt under any joint distribution for xt and yt that have those marginals. That's the coupling inequality. It's very simple to prove, in fact, it's a few lines. And then in that case, the probability that xt is different from yt is exactly the same as saying that the meeting time will occur afterwards. Because once they stay together, once they meet, they stay together. So if they're different, it means they haven't met. And so that means that if you find a way of constructing chains that meet, and you can say something about the distribution of the meeting times, then you obtain an upper bound on the convergence of the chain. So that's really the key idea of the coupling method for Markov chains. And so it turns out to have been quite successful and continues to be successful. Here's a reference by Mark Jerome that provides a really nice introduction to the idea and with applications to mostly Markov chains that have been used in combinatorics to count things like colorings of graphs, for example. But it can be used in many settings, like in statistical settings to study Langevin-based method, Hamiltonian Monte Carlo, and so on. It can also work for other metrics than TV. It's not intrinsically linked to TV. For example, if you have chains that don't meet but just get closer to one another in expected distance, then you can obtain upper bound on the Wasserstein distance between pi t and pi. And so at this point, everything here is theoretical because we have assumed this new chain y starts at stationarity. And of course, we don't know how to sample from stationarity if we're doing MCMC in many cases. You could imagine sometimes you know how to do it, but it's too expensive, so you're doing MCMC anyway. But generally speaking, in challenging MCMC scenarios, we just don't know how to sample from that. Okay. So here's an example of just to show how precise and simple a coupling-based analysis might be. So this is called a donkey walk because it's been called like that by Gérard Letac in his 2002 paper. And it's called a donkey walk because it's representing a Buridan's donkey. That's a donkey that hesitates between going towards the bucket of water or going towards the food. And so it does one step towards the right and one step towards the left alternatively, and it never reaches, unfortunately, either. But it proceeds as a Markov chain. So we imagine a state space is, say, 0, 1. And the recursion is basically scaling and translating with beta variables so that the Markov chain remains on 0, 1, doing one step towards the left, one step towards the right. And this is parameterized here with 2 integers and 0 and 1. As it happens, this also is related to doing Dempster-Schaeffer analysis of categorical data, and that's where I've encountered this chain in our collaboration with Robin Gong, Paul Lefsen, and Art Dempster. So you can see the link in that paper, but it's been around in the applied probability literature as a Markov chain. And so if we want to analyze this with coupling to decide to understand how many steps it takes for the donkey to be close to its stationary distribution, we can introduce 2 donkeys, basically. One at stationarity, here is z tilde t, one not at stationarity, for example, starting just in the middle of the interval. And then we evolve them both with the same random inputs, so the same beta scalings. And then it's very easy to compute the expected distance between the two at time t. It's a simple calculation of expectation of beta random variable. So really in a few lines, you end up with a very precise form of an upper bound. You can see it's very explicit in the parameters n0 and n1. Here on the Wasserstein 1 distance between pi t and pi. There's also a term on the right-hand side, the expected distance at time 0, which here is easily bound by 1 because the 2 donkeys are in the interval 0, 1. And so it turns out also here, and that was pointed out by Guanyang Wang, who is an assistant prof in Rutgers University, that you can prove that this is the sharp rate of convergence. That's not always the case, but this in fact is the sharp rate. And really obtained in a few lines. And so in this particular case, you could actually select t, if you have the knowledge of n0 and n1, exactly so that your Wasserstein distance is less than epsilon. You really can compute things precisely. Again, maybe bounding the initial distance by 1, which doesn't look very crude here. But that's not typical, right? So typically when you have such upper bounds, they involve some numbers that are not available to the user in statistics. And so to the best of my knowledge, few statisticians when running MCMC can find very concrete guidance in the literature. The theoretical results are very helpful, not only qualitatively, but to know, for example, about the impact of the dimension on the scaling of a Markov chain and things like that, but they don't really give you exactly information that in order to obtain an epsilon error, you have to run exactly these many steps. So this is not representative. But we would like to have a method, of course, that would give us this concrete guidance. So we'll focus next on a subclass of couplings called Markovian couplings. So those are the ones where X and Y evolve according to a Markov kernel, here denoted by P bar, that satisfy again the marginal constraints that X follows the Markov chain with transition kernel P and Y as well. But jointly so that the 2 chains can meet with some probabilities, at least from some states. And then once they've met, they remain together, and that's called a faithful coupling again, in the parlance introduced by Jeff Rosenthal. And that's one of the few links between Romance and Markov chains. So the goal will be to design those coupled kernels that induce short meeting times. And then we'll see what we can do concretely to obtain this guidance on the convergence rate of the chain. So going back to this example with the Gibbs sampler for the location of a Cauchy. This was the 2 steps of the Gibbs sampler. So how do we design a coupling in such a way that 2 chains, those 2 chains which are simple but yet on a continuous state space, are going to meet exactly? So you start from 2 different thetas, and you're trying to design the evolution in such a way that the 2 next thetas, theta prime 1 and theta prime 2, will possibly become exactly identical. So here's a possible construction. You start from theta 1, theta 2. For example, you generate the etas using common uniform variables that you transform to obtain exponentials using the logarithm. At that point, you will not observe the same etas, right, because you will scale them with different values. But then once you have the 2 etas, you can sample from the 2 corresponding normals that have a different mean and a different variance using a so-called maximal coupling algorithm, which is few lines, in fact, it's like a rejection sampling algorithm, which I'm not actually showing here. Happy to talk about it more. But it will have the property of satisfying the marginal constraints. So the theta prime 1 and theta prime 2 will follow the right normals. And on top of that, the probability of observing a meeting will be maximized. And we know that the maximal value is in fact 1 minus the total variation distance between those two normals. And you can do that for any distribution that are tractable. That is, that you can sample from and evaluate the density of. There's an algorithm, there's at least one algorithm that is applicable in that. So if you haven't heard about it, it might sound like quite complicated, but if I'm telling you, try to use rejection sampling to do that, you will probably manage to figure it out. But basically, the idea is to sample from one of those two normals and try to accept that draw as a draw from the other normals, and then it will be a meeting. But if you don't manage to accept, you have to do something else so that marginally the constraints are satisfied. And you can do it, it's an exercise in applied probability. And so if you manage to do that, then you observe two chains here, one in blue and one in black, but you see that meet quite quickly in a few dozen iterations. They become exactly identical and then continue to be identical. So now we have a certain meeting time. Of course, if we rerun this, we'll observe another meeting time. So there is distribution of meeting times. But here, neither of the chain was started as stationarity. They are both started from the pi0 distribution that we would use to generate our initial choice. And so you can not only do it for this simple chain, but it turns out you can do it for various chains. And so those are papers considering this problem in various settings. The first one is with my former student, Niloy Biswas, and Anirban Bhattacharya and Jim Chandro. And we look at Gibbs samplers for Bayesian regression with the horseshoe prior, which is known to be a bit challenging, but there have been Gibbs samplers that have been proposed for this problem. And we've tried to couple those Gibbs samplers. This is available on arXiv. And it works with even large dimensional problems if the coupling is set up appropriately. And those are other papers on the topic. There's Ruiz et al. That looks at the context of variational autoencoders. Tripp et al. Looks at the problem of basically mixture models or directly processed mixture models, where the MCMC is on the space of partitions to try to cluster your observations. And they do couplings of those Gibbs samplers. And then the last one is recently also on arXiv. It's about phylogenetic inference. It's an MCMC on the space of phylogenetic trees, and they've managed to come up with coupling strategies for it.
So is this T going to give you information about the other T that you actually want, the time to the stationary?
Yeah, exactly, which I haven't yet at all. And so you now need to connect because we're not assuming that one of the chains is at stationarity. So we're not quite in the original coupling construction. And so, but still we can find information about the convergence rate. And so, in fact, that's what's coming next. Sort of different uses of those couplings of MCMC algorithms. So the first one, the first one we looked at chronologically was the use of those couplings to obtain unbiased estimators. And then I'll move on to convergence diagnostics. The estimation of nested expectations. And I'll give some examples, for example, normalizing constant estimation. And the last one is asymptotic variance estimation in the CLT for the original MCMC algorithms. And it's all powered by the capacity of doing those couplings of Markov chains. So the only twist in this part is the fact that we're going to sample the two chains, again, not starting from pi, really starting from an arbitrary pi0, but with a lag. So that's the twist here. We create a lag between the two chains. So we advance the first chain x L steps using our MCMC algorithm. And then we have xl and y0. And we advance this pair to obtain xl plus 1, y1, xl plus 2, y2, and so on, using this coupling. Some coupling that we have managed to do for our MCMC algorithm of interest. And so then the meeting would occur in such a way that then xt is equal to yt minus l from the meeting time onwards. So that's the twist. But still, xt has the same distribution as yt at time t. Why is that? Because the coupled kernel satisfies the marginal constraints. And so YT has the same distribution as XT, which is the distribution after T step of the Markov chain. So if you can do that, you have this classical now telescopic sum argument that's due to Peter Glynn and Changhan Ri in the context of Markov chain, and previously was introduced by Peter Glynn in the context of multi-level Monte Carlo. And this is the trick. So you have the expectation of interest here, the expectation of H with respect to pi. You write this as a limit of the expectation of xt when t goes to infinity. You write the limit as a telescopic sum. So you say it's I start at an arbitrary time k, and the expectation of h of xk, and then you add the expectation L steps later, and you remove it. And then 2L steps later, and you remove it, and so on and so forth. So it's a telescopic sum. Okay. Now, using the fact that xt and yt have the same distribution at time t, any expectation with respect to some xt, you can replace by an expectation with respect to some y at the same time t. So now you see appearing in the expression a difference between x and y, but with this lag. And of course, that's why we created the two chains with this lag. So that now if they meet, we can hope that we can swap the limit and the expectation and obtain thus an expectation of an infinite sum equal to our original expectation of interest. And this infinite sum, in fact, can be computed in finite time, because from the meeting time onwards, all those differences between x and y with the lag are equal to 0. So really, that's the nice thing about this trick, is that you're basically constructing an infinite sum after finitely many steps. You can basically stop computing at the meeting time because you know all the subsequent terms would be equal to 0. And so, in fact, we don't propose to use that estimator, but a slight variation of it. So there's more notation. This is what we call the unbiased MCMC estimator in a paper with John O'Leary and Eva Chade. This is basically a variance reduction from the previous idea. And the appeal of this is that the estimator is of the form of a standard MCMC estimator in the first line. This just looks like a standard ergodic average if you did m steps in total and you discarded the first k steps. But you have the second term, which we call the bias correction term, because it makes the entire thing unbiased. And the second term involves those differences between the chains with a lag and with some weight here. So you have to choose those integers that appear here, L, K, and M, that are user chosen. And of course, you have to choose, as always, maybe you have to tune your MCMC kernel and the coupling of it. And there's a lot of open questions about how to tune those things efficiently. Of course, there's no more bias, so the mean squared error is the variance. You care also about the cost. You care about the mean squared error and the cost. And those tuning parameters will have an impact on both. And the benefits of using larger lags was pointed out by Paul Vanetti and Arnaud Doucet in the discussion paper. So now we actually recommend using always a larger lag than 1. Originally, we used a lag of 1, as in McLean and Reed. And also, in fact, you have different assumptions that have been proposed for the tails of tau. So, of course, you need assumptions to justify the swap between the infinite limits, then the limit and the expectation. And that translates into assumptions on the moments of h under pi, but also on the meeting time. And so originally it was geometric tails assumptions, and then we relaxed it to polynomial tails with Lawrence Middleton, George Delitanidis, and Arnaud Doucet in that paper. And those are available online. That was useful to cover the case of particle MCMC, for example, which is known to be sometimes a polynomially ergodic. So it leads to polynomial tails for the meeting time.
Any polynomial? You need a certain order?
You need a certain order, yes. But you need a certain order to have a CLT first. And so here also, to have a finite variance, you need a certain order. And we're doing a crude job. And we were happy to say for some polynomial tails, it's okay, but we don't know what the minimal order would be. Okay. Then, of course, there's an interplay between that, between the tails of the meeting time, which have nothing to do with the text function h, and the moment conditions on h. Yeah, so all of those results are basically sufficient, but we haven't found any necessary condition. So that was okay, unbiased estimation, but we still haven't really answered the original question of, okay, my original MCMC estimator, how long should I run it? And so that's what we're trying to do in this this part, diagnostics of convergence. But it's really the same reasoning. So one way of looking at it is to say, we're looking at the marginal distribution at time t, the limiting distribution pi, looking at the TV. You're reusing the same idea of this telescopic sum, and you apply the triangular inequality directly on the distributions here to obtain this infinite sum of TVs. You know, they're basically TV between pi t plus L, and then between pi t plus L, pi t plus 2L. And you go towards infinity in steps of size L, basically. And then you use the coupling inequality for each of those TVs. So you find that they're each less than the probability that some xt plus j is different from yt plus j minus 1L for any variables xt plus jl and yt plus j minus 1L that would follow those marginal distributions. And then you run couple chains and you estimate all of those probabilities by indicators. Right? And that's unbiased. And you can estimate infinitely many of them with only finitely many steps, because you know once they meet, they will continue to be together. So you know that indicator, when it moves to 0, it stays at 0. So it uses exactly the same lag construction of the chains as before. And when you rearrange the terms, you find that what we're already using as an upper bound is basically the expected number of non-zero indicators in that infinite sum. And that's simplified. So the expression you have here is an expectation of this function of the meeting time, of the time t of interest, and here of the lag. And so what we are proposing to do then is approximate this expectation with a sample average by replicating the simulation of the meeting time tau. So yeah, which is kind of nice because, well, of course, it requires again some work to obtain those meeting times, but it's always this one-dimensional integer variable, irrespective of the complexity of the original MCMC algorithm, and it gives you a curve that upper bounds this TV.
Is that what they were talking about, using larger lags? Because you want this to be lower.
Yeah, exactly. So you want this to be, for example, you know, the TV is always less than 1.
Yeah.
So it turns out that if you use a small lag, usually for small t's, you will have an upper bound that's much larger than that's obviously not giving you any information.
Yeah.
Even though it goes to 0 when little t goes to infinity for any L, but we find tighter bounds with larger L.
Yeah.
But it also helps in the variance of the unbiased MCMC estimator. So it's generally a good idea to use a larger lag. Of course, how large? Large open.
Sure.
So we start usually with 1, and we do simulations, we obtain bounds, and then we choose a lag that looks like a large quantile of the meeting times. And it turns out this upper bound was refined recently. So this one is coming from this paper by with Niloy Biswas and Paul Vanetti. So this is the same one as in the previous slide. So basically, it's in the form of an expectation of this variable that is just a transformation of the meeting time. So that really is a link between the simulated meeting times and the mixing time. That's this is the form of our connection between the two concepts. It turns out you can refine automatically this bound. Right? You can in fact write this upper bound. That's from a paper by Radu Krayu and Shaoli Meng. And this is always less than the expectation, because the expectation is the sum of the probability that j is larger than little j, the form of expectation of a non-negative integer, non-negative random variable, using the integral of the survival function. And so if you take the minimum between this and the CDF of that variable, you have something that must be smaller and so a tighter upper bound. Although the gains are not obviously large, but they could be, I guess. So back to that example, just to be concrete. We take that chain, and from this, it wasn't obvious how many steps it takes to reach stationarity. But if we generate lots of coupled chains until they meet, and employ the meeting times in our upper bound, we obtain a curve like this, a very concrete curve that suggests that, of course, under the hope that the expectation is well approximated by the sample average, which of course sometimes is not going to be the case, but under that sort of assumption, which we try to get confident about by initializing from very well spread initial distributions, for example, that minimize the chance of having missed completely some part of the state space. But then you would really have a concrete guidance that says, for example, here 50 steps is enough to get really close to stationarity. So in a simple example like this one, we can check, whether that's plausible, whether that's tight or not. So what we've done simply is simulate many chains for 10 steps, and then 20 steps, 30 steps, 40 steps, 50 steps, look at the marginal and see if indeed 50 is a conservative estimate or not. So you see here, after 10 steps, I don't know how clearly you can see it, but the histogram doesn't quite match the density. There's too many points on the left and not enough on the right. And so that means really 10 steps is not putting the chains at stationarity. 20 steps, it gets closer, and as we increase the number of steps, it gets closer. And indeed, at 40, if you really zoom in, you would see that there's a bit too many, there's too many points on the left and not enough on the right. But after 50, it seems like, it looks like the Monte Carlo variations are a bit bigger than the systematic difference. So the original, the bounds obtained by meetings seem to be quite sharp in this case. Of course, that will completely depend on how you design the coupling. So here it seems like maybe this coupling that was pretty naive, but it does the job. So that was should I stop here maybe for questions? Continue.
So for the approximating the expectation, which I guess is the crucial part of this actually being a reliable number.
Yeah.
Is there maybe more you can do, things like concentration inequalities or something to try and get
yeah, that would be great. Yeah. So what we get is random variables that have the expectation that you like, but they're not compactly supported. You don't know their variance, you can estimate their variance. Mm-hmm. So that rules out certain abuse concentration inequalities, but they are still independent, they're still IID with the expectation of interest. So it's, certainly maybe some use of robust mean estimation compared to just sample averages that could be useful. If the distribution that you are observing is very non-Gaussian, we know that the sample average is not the optimal estimator of the expectation, and so maybe there are some gains there. Fundamentally, and that's kind of I think the problem with any MCMC is that you always have the possibility that you started all of your chains in one mode and there was another mode very far away, and so then it doesn't contradict the unbiasedness, because once every billion times you would observe another meeting time that would be very different. But yeah, there's always this possibility. So apart from really trying to think about what is a widespread initial distribution, which is not obvious, of course, in general, depending on the space. But apart from that, I don't really know yet what to propose or what to suggest. So another thing that's so originally really we worked on these unbiased estimators with the primary motivation of parallelizing the calculation, because in the world of parallel computing, MCMC is iterative, so it's it stands at odds with the trends in computing architecture, and so we were thinking that was really the motivation also in the multi-level Monte Carlo work before us, and even in the perfect sampling work in the 90s. One of the nice things about being able to have the right expectation is that then you can do a lot of independent replications and have this obtain the precision that you would want, arbitrary precision that you would want, as you add more and more computers. But then we sort of also observed other byproduct of the unbiased property that are more that we didn't anticipate. And so one of them is the capacity to estimate nested expectation. I'm going to try to give examples. But just I'm going to rewrite the previous estimator without test functions. So instead, that's the previous estimator, but instead of the test function evaluated at some x's and y, there are Dirac masses, point masses at those x's and y's. And that sort of suggests that the estimators we obtain is a sign measure, in fact. A sign measure that has a number of atoms and weights, and there are some negative weights you can see in front of the y chain. And so you can sort of summarize this as pi hat is equal to a sum of omega n delta zn, where omega are the weights. Then they can be negative. And the z's are atoms that are generated by, they're either some of the x's or some of the y's. And the unbiased property then reads that if you take an average with respect to your sign measure, a weighted average with those possibly negative weights, then in average, this has the correct value with respect to the distribution of the sign measure. And this is helpful in understanding how we're going to be able to estimate multiple integrals, basically. I'll give some examples. The first example is to do with this distribution, sometimes called the cut distribution. So imagine you're doing Bayesian inference in a model that is made of two different components. A component with prior P1 on the parameter θ1, and there's a likelihood P1 of Y1 given θ1. And there's another model with parameter θ2, theta Y2. But the definition of the second model involves a value of θ1. Okay, so for example, you have a θ1 represents maybe some missing data, and you have a mechanism to sample some missing data. And then given the imputed data, now you have a model, you do some sort of regression on your computed data. And so you define your regression using the imputed data. And overall, you have those two models that you could fit jointly. But in fact, many people would not fit them jointly. They would like to propagate the uncertainty of, say, the missing data onto the final estimate without necessarily using the second stage to change the way that the missing data is imputed. And that leads to the so-called cut distribution. So it's defined as the marginal distribution in the first model for θ1. And then you sort of multiply it by the conditional of θ2 given θ1 and y2 in the second model. So this is not the standard posterior in the joint model. It's a really nice paper by Plummer in JCGS on cuts in Bayesian graphical models. Just plug in here some advertisement for work with Emilia Pompey that we put on archive last week on some frequentist properties of those cut distributions and using the posterior bootstrap to approximate the cut or distributions related to the cut. And so this sign measure business arises because if you want to estimate the cut, what you could do, I should go back actually and say, how would you do MCMC on that? It's not so obvious. In particular, because the second posterior has a normalizing constant that depends on θ1 and that you typically don't know how to evaluate. And so what you could do is MCMC on the first model. So you sample from the first posterior. And then for a certain number of realizations of θ1, you do MCMC conditionally on θ1 for the second model. But now you are in a sea of MCMC. And so it's not obvious to compute, for example, confidence intervals on the final estimate. You have those many chains, each targeting a different distribution. And so you have to do convergence diagnostics for each of them and so on. And so on the other hand, unbiased estimation, I think, provides an appealing solution to this problem, where we will directly obtain unbiased estimators of this cut distribution. So then we can replicate this in parallel and compute confidence interval in a straightforward manner using the central limit theorem for IID variables. So without having to worry about convergence of many different chains. So how do we do that? Well, basically we do unbiased MCMC for the first posterior. So we obtain lots of θ1s and weights. And then we can randomly select some of those θ1s and do unbiased MCMC on the second stage for those θ1s. And by the law of total expectations, or the tower property, if you like, you have unbiased estimator for the entire thing. So that's a proposal. You do unbiased MCMC for the first stage, and then you select an index among the atoms. according to some probabilities, which again would be something to tune, but you can say 1/n uniform on all the integers, for example. And then you do unbiased MCMC for the second stage. And by the law of total expectation, this is unbiased for the cut distribution. And you can add, imagine adding another model, but then you have 3 layers of unbiased MCMC to do. So again, like, there's a lot of tuning actually when you do that, because you have to choose those lags and everything. But at the end of the day, if you get an unbiased estimator and you're reasonably happy with its cost and its variance, then you have a practical way of approximating this cut. Another application of this idea, apart from the cut, is if you're interested in, I'm going to go quite quickly on this because I want to talk about asymptotic variance. But basically, you can write by the so-called path sampling identity or thermodynamic integration identity. You can write the log normalizing constant as an integral over 0,1 of an integral with respect to a distribution here pi lambda, where lambda indexes a bridge of distributions between pi 0 and pi, for example, via tempering. And so again, by writing it as a double integral and doing unbiased estimation at each stage, you have an unbiased estimate of log z. Whereas, for example, SMC samplers provide unbiased estimate of z and not log z. And that's not clear that it's better or worse, but it's funnily different. So we had an early draft on this with Maxime Richard and Matej Pillai. We were working on an update with the help of Emilia. Okay, and I want to finish with asymptotic variance estimation, just for 5 minutes. But if there are any questions, I'm happy to instead answer any questions.
I have a question about that. Can you leave it to the end?
Well, go ahead.
You haven't. What happens with high dimensions? Theta. I mean, all your theta stuff being one-dimensional.
Yes. Yeah. I've just flashed this one slide where I mentioned these other people's work.
Yeah.
So, I mean, I think the question that you're asking is working for challenging MCMC settings, because it can be high dimensional and very simple, and it can
yeah. Let's say, I mean, because usually you assess convergence, and often it's one variable that might be one that's not converging. The other parameters are converging. So, or marginal likelihood might look okay, but there's something that's not converging. What would you couple? Yeah.
So here you have to couple the whole chain. So if one component was slow, it would take a long time to couple. The whole thing would take a long time to couple. So you're measuring really the entire convergence.
So you really need to couple all the parameters. There's no way to just couple one.
No, because if you do, say, a Gibbs and you couple one, but the other ones are not coupled, then the one that you have successfully coupled might decouple. Because the conditionals are still different because of the other parameters. Okay. So it's only coupled, it's only, the meeting time occurs when everything is equal. And in the example of the regression with horseshoe priors, we tried up to 100,000 dimensional. And it takes 1 minute per step of MCMC. But thankfully, the chains couple in about 500 steps in average. And so it's a question of hours, maybe. That's the joint work with Niloy Biswas, James Chandro, and Anirban Bhattacharya. We have different examples there, and yeah, P goes to 100,000 in a GWAS study. And that's painful, we have to wait hours. Another example that is still quite high dimensional in dimension 4,000, but there's only 70 rows in the data set. So n equals 70, p equals 4,000. That's really nice because you can work on it with your laptop and it meets in a matter of seconds. But that's, yeah.
Sorry. How much case specific is the design of
the coupling?
In this result?
Yeah, so it's really algorithmic specific, right? So we use the same for the different data sets, but it's entirely built around the Gibbs sampler, which itself was designed for a regression with horseshoe priors. So it's it's very specific to that. And just quickly, by now, when you worked on coupling more in the context of SMC, we've worked with Jeremy Heng on Hamiltonian Monte Carlo, and some other people in Edinburgh have done a more fancy version of Hamiltonian Monte Carlo. So that works really well for high dimensional but nice, smooth targets. I think we went to 100,000 dimension on the Gaussian there.
Okay. And there was one paper that you showed that was doing mesh models. Does that
Yeah, the work
well?
of Tamara
Yeah.
and our colleagues, our collaborators, which is on archive as well. Yeah, I think the problem there is like many MCMC algorithms actually are not working so well.
Yeah.
And so, you know, if your MCMC algorithm mixes slowly and we're getting upper bounds on the mixing rate, we're going to wait a long time.
Yeah.
And none of this accelerates the MCMC that you start with. And what they deal with is the label switching issue, which is an extra complication for the coupling. So they have a nice solution for that. But ultimately, if the MCMC sampler that you're considering mixes slowly, of course, Woody will tell you that it mixes slowly, which is information, right? So in the context of PMCMC, I would say I thought it was quite challenging also, the paper with Middleton et al. You know, we have like state space model with like, we have an example with 3,000 observations and we have to impute the latent process. So there's 3,000 steps there where we use controlled SMC, etc. And then do MCMC on the parameter space where there's a particle filter at every step. And that took also, I think it was a naive implementation, but it would take 30 seconds per step or something. So, you know, we used the cluster and still took hours. But so I would claim that it works in certain challenging problems. But if you have a new challenging problem, you have to work specifically on an algorithm that hopefully works well to begin with, and then a coupling. And in terms of how do you design the coupling, there are like guidelines, you know, you can try things like common random numbers, maximal couplings, optimal transport couplings, but you have to find a way of putting things together, and there's a million possibilities typically. It's exciting, but it's not obvious by any chance. In the works on the high dimensional regression, we use a coupling that looks at the distance between the chains, and depending on the distance, we employ a certain coupling or another one. So it took some effort, and the first attempt we did didn't work at all. The last thing is this connection with the asymptotic variance. So the connection is via the Poisson equation. So we write pH of x first, a function that is the expected h of x1, given that x0 was at x under the distribution P, the Markov kernel P. Now with this, the Poisson equation is this equation. So h tilde is a solution if h tilde minus ph tilde is equal pointwise to h minus pi of h. And then we, instead of saying h tilde is a solution of the Poisson equation associated with h and p, we just say that h tilde is fishy. And so under the summability condition, this function, for example, is fishy. And that is reasonably easy to check once you're given the form of it. And that is well known for a long time, in particular in obtaining central limit theorems for ergodic averages. So here's how it works. You want to get a CLT for your Markov chain average. So you're looking at the sum of h of x at time s minus the limiting value of the average. And then you use the solution, h tilde. So you can write h minus pi as h tilde minus ph tilde. And so you sort of put the boundary terms on the right-hand side, and you have this sum of differences that in fact have expectation 0 given xs minus 1. And so it's nice because then you can employ the so-called martingale difference sequence argument. If you apply a central limit theorem for martingale difference sequences, and you get directly the form of the asymptotic variance as the expectation of the square of those terms under the. So it's E star because it's under stationarity, at stationarity. So x0 follows pi here, and and x1 follows, given x0, follows the Markov kernel P x0 dot. That's explained, for example, in the many books on Markov chains, such as this one by Duke et al. And so what's kind of the connection with coupling is that there's a fishy function that looks like this. So you pick an arbitrary y on the state space, could be anything, like say the origin of the state space, if there is one. And then this function that maps x to the infinite sum of the difference between the conditional expectations t steps ahead, starting from x or starting from y. That's a solution of the equation. And when you look at it, you just want to estimate it with coupling. You just can't help doing it. So you just start two chains, one at x and one at y, in such a way that they meet. And then you'll be able to estimate basically time-wise all those expectations. So that's exactly what we're proposing to do. And the estimator is simply, so there's no lag here. You want the function evaluated at some x, you have fixed a y, and you start to chain from x and chain from y until you run them until they meet, and you just compute the sum of the differences up to that time. And that's an unbiased estimator of the function. Which is kind of nice because those functions have been in the MCMC literature, but it's not necessarily easy to see what they look like and to estimate them. And so this is a direct way of estimating them. And so then, massaging a bit the previous expression on the asymptotic variance, we can write it in this way. So there are three terms, but the challenging one is the first one. It's an expectation with respect to pi of a function that itself depends on h tilde, which we need to estimate. So again, it's a nested expectation type of problem. So you can unbiasedly estimate pi with some measure pi hat. And then for some atoms, you can estimate the Cauchy function at those atoms. And you can put that all together into an unbiased estimate of this asymptotic variance. So it's kind of the same thing nested at Monte Carlo. I write the whole algorithm here. It looks a bit ugly, but basically, you need to actually estimate two unbiased estimators at each step, because to estimate the square of pi of h without bias, you compute two independent estimates and you take the product of them. And so we obtain two sign measures, and for one of them, we compute estimates of the Cauchy function evaluation at some atoms. I'm going to wrap up very soon, so bear with me just one sec. Basically, you can estimate all of those terms without bias. And we're hoping to put something on archive. That's with Randall Duke, Anthony Lee, and Dutika Vats. This is kind of a diagram that I don't know if it really helps. It's saying that the first stage is obtaining those sign measured, so atoms with positive or negative weights. And then you sort of randomly select some of them. And at those, you estimate the Cauchy function by running two chains, one from that x and one from this arbitrary point y that we have defined once and for all. And you run them until they meet, and etc. And so then I'm going to probably stop. I have numerical results on this if you're interested. Comparison to classical stuff like CODA spectrum 0, CODA spectrum 0 AR, initial sequence estimator. But just to wrap up, so those were topics that are very sort of basic in a sense, because it's not about a new algorithm for a new challenging application. It's really, you have MCMC, it's an iterative method. You have to choose the number of iterations to perform. Many people have worked on the topic, but there are still like gaps in providing concrete guidance to practitioners. And so I hope to convince you that with couplings, you can make progress really in practice. For non-trivial cases, you can obtain, not necessarily super strong guarantees, but some indication of how long it takes for the chains to converge and how to compute the asymptotic variance also, so how to compute the confidence intervals. And so here I just list all the collaborators in the different works cited before. Thanks for your attention.